Alright, in this lesson we're going to be looking at the purpose of logarithms. Specifically, what are logarithms good for? What was the original intent for logarithms? And what are some properties of logarithms? That kind of happens as we have this discussion. So, let's go ahead and get started. The short answer is logarithms are good for science and engineering. Specifically, when you've got to multiply, divide, or take some number to another power. So let's say you just had something that seems pretty basic to us nowadays, 2.87 times 8.93. Maybe you had some quantities you were multiplying in some sort of context a couple hundred years ago, and you needed to know that. And if you didn't have a calculator, if you didn't have modern tools, then you'd have to go back and do the 3-digit times 3-digit multiplication. 3 times 7, 3 times the 8, 3 times 6, or 3 times the 2 to 6. Oh my gosh, no one wants to do that, especially if you have a whole lot more digits here. So what we're going to do is, via some clever math here, we're going to turn this number, 2.87, into a power of 10. And we're going to do the same thing for this one. You're like, why in the world would you want to do that? Well, because we can turn this annoying multiplication problem into an addition problem. And that's always a good thing. So we're going to turn that 2.87 into 10 to the 0.4579. So it's not even 10 to the first. It's like 10 to the decimal point. But that's, if you take 10 and raise it to the 0.4579 power, then you'll get 2.87. If you take 8.93 and that's equivalent to 10 to the 0.9509 power, or exponent, I guess. So you're like, okay, how did you get these? Where did you get those numbers? How did you figure out what the exponent was if you have 10 as the base and you want to get this number right here? How did you get that number? Well, it depends on what time frame you're looking at. If it was in the olden days, then you used a table. You used a logarithm table. If it was quasi recently, so a couple decades ago, then you could have used a slide rule. If it's nowadays, you'll just use a calculator. Here's what some of those olden logarithmic books looked like. It is these tables, these books of tables that I guess math monks would sit around and write down the different values and do the calculations. We don't really need to do that. We're just going to say, okay, we want 2.87 to equal 10 to some power. Look familiar? Show me the exponent here. What's that exponent? Well, we just say log base 10 of 2.87 is what? What is that exponent? So I say use a calculator, and you get 0.4579. So I've turned this multiplication of this number times this number into multiplication of this number times this number, since those are equal. And we know via our properties of exponents that when you have two numbers multiplied together and they both have the same base, then you can just add those exponents. So 0.4579 plus 0.9509. See, we've turned that annoying multiplication into just an addition problem, plus a little lookup here at the beginning. So that turns out to be 1.4098. Now, we'll need to turn this number, this power of 10, back into an actual number. So something around 2 and some stuff times 8 and some stuff. So if we round it up, it's almost 3 times almost 9. So something a little bit shy of 27 is what we're kind of expecting. And in fact, what we get is 25.70. So the exact answer is 25.6291. So, like I said, just a little bit, almost 27, not quite 27. You might say, hey, how did you do this? And the answer once again is, well, if you didn't have a calculator or slide rule, you'd have to go to another log table or anti-log table that would you've looked up 10 to the 1.498 and it would tell you this number right here. And so basically replacing this annoying math, long multiplication problem with just a look it up in a table, do some addition, then look this up in a table. Which if you had multiple operations and things like that, this could, be a real time saver. So this is close enough. All right. Now, we're not just going to look and see what people did and what purpose logarithm served. And it primarily was used for doing calculations, arithmetic on, lots of digits here. But there's some interesting properties that arise when we when we look at this, so notice those exponents, the 0.4579 and the 0.9509. So those were exponents, and that gave us this this number right here, the 1.4088 or 98. I can't remember which one exactly it was. Anyway, so that was the exponent. This was the exponent. This turned out to be the exponent. So those exponents were the results of a logarithmic calculation. So we could say, that exponent right there is equivalent to log base 10 of 2.87. Log base 10 of, not 2.87, the 8.93. And this was the result of log base 10 of that final answer of, that 25.70, or of the product of those two numbers, 2.87 times 8.93. So if we look at this, we have log of this thing, which we can call A, plus the log of this thing, which we call B, is equal to the log of the product. So it's basically saying exponent plus exponent equals exponent. That's exactly what we would expect. That's the property of exponents, and that has its correspondence here in the property of logarithms. That is, log of A times B is equal to log A plus log B. And of course, I'm not writing a base here, but we're going to assume that the base here is always the same. If you have different bases, then these properties do not hold. You have to have the same base in every case here. All right, so there's an addition property. Another interesting property kind of arose whenever we wanted to take a number to a power. So like 5.42 cubed. So that would be 5.42 times 5.42 times 5.42. And so you can imagine how annoying it would be to actually calculate this by hand, 3 digits times 3 digits times 3 digits. Oh my gosh, that's even worse than the first one. So let's make life easy for ourselves. Let's just go ahead and turn this number into 10 to an exponent. So 10 to the 0.734 times 10 to the 0.734 times 10 to the 0.734. Because if I do that, then I know based on my properties of exponents, I can add those exponents right there. So 0.734 plus 0.734 plus 0.734. So 3 times 0.734. I can do that very quickly. That's some calculations. That's 10 to the 2.204. I go ahead and look that up in the table, and I get about 162.18. If I were to use a calculator right now, the exact answer is 159.22. So once again, kind of close enough. So once again, we notice that we had 3 times that exponent, okay? And that exponent, 0.734, was the result of saying, 10 to the 0.734 is equal to 5.42. So instead of writing 0.734, we could put log base 10 of 5.42 inside this parentheses. So 3 times the log of that number was equal to the exponent that we got for the answer. And instead of writing the answer, well, I guess I could put the exponent right up here. So that exponent was 2.204. And then if I wrote a similar statement here, I could say, okay, that exponent is equal to the log base 10 of 162.18. So 10 to this power is equal to 162. But that 162 was the result of the 5.42 cubed. All right. So if you look here, we have some multiplier times a logarithm. So C times log of A is equal to log of A raised to that power. Of course, just like in that other one, we normally write this side first when we're summarizing our properties. So go back here to the power property of logarithms. We have log of any base of A to the C is equal to C times the log of A. So it really means, practically speaking, you just pull that exponent down and put it there as a coefficient, and that's a legitimate mathematical operation. And we just saw why. If you're not sure, you can rewatch that part of the video. And of course, we've got to have some division property. So once again, we have two numbers divided by each other. We really don't want to mess with all of this, doing that long division. So let's rewrite 9.8 as some power of 10. So 10. So log base 10 of 9.8 is 0.991. So that's the exponent that you would have to have. let's take the logarithm of the bottom there, or the denominator. So log base 10 of 1.12 is 0.0492. So I think we're going to need to go to another page here. So that means that 10 to the 0.9991 power is equal to 9.8. And 10 to the 0.0492 power is equal to the 1.12. So I can substitute these exponential expressions here, 10 to the 0.9991 and 10 to the 0.0492. And then I know that my division here, 0.991 minus 0.0492, it's going to be 0.499, which I can type in the calculator or go to that log table and or anti-log table and look it up. So it's approximately 10 to the 0.95, which is 8.91. The exact, if I were to plug this in the calculator, I think it's 8.75 or something like that. So pretty close. And we're doing some, there's a trade-off. Instead of having to do long division, like I said back in the day, we're doing a table lookup, a subtraction, and then another table lookup. And there's a trade-off. You're not getting the exact answer, but you are hopefully saving yourself some time there. So looking at this process, we have exponent minus exponent equals that exponent. So instead of writing those exponents, I'm going to write the log expressions there. So do a substitution. Log base 10 of 9.8 minus log base 10 of 1.12 equals that right there. That's the log base 10 of 8.91, which 8.91 was the division of those two terms here. So we have log base 10 of 9.8 minus log base 10 of 1.12 equals log base 10 of 9.8 divided by 1.12. So there's your A and your B, there's your A and your B. We write log A minus log B equals log of A divided by B. We normally write the right side first. Going back here to our summary, we could say the log of A divided by B is equal to log A minus log B. And that's great. There's just a few more additional properties of logarithms that we're going to look at very quickly. So 5 to the 0, we know that's equal to 1. 10 to the 0, that's 1. E to the 0, that's 1. Anything raised to the 0 power by definition is 1. So b to the 0 is 1. If we write this as a logarithm statement, we would say log base b of 1 equals 0. So if you have log base 5 of 1, log base 10 of 1 is 0. Sorry, log of any base of 1 is equal to 0. So if you have log base e, so natural log of 1, 0. That's a good property to know. Here's another property of logarithms. It's helpful. So let's say you've got y equals 5 to the x. This is an exponential function. We know that that is going to look like this exponential graph here. If we convert that into logarithmic form, that would be log base 5 of y equals x. We normally don't write our graphs as y as a function of x. We normally have, x as a function of y. We normally have those switched around. So just to show us the normal way that we would write a logarithmic function, be y equals log of x. And as we talked about before, that function is going to look like this, or that graph rather. And we noted that the domain are all x values greater than 0. Okay. So if the domain is greater than 0, then that means if you have the log of -3, doesn't exist. Natural log of -2 doesn't exist. That is a helpful property. And the third helpful property is, well, let's figure out, what if you have the log base 5 of 5? What if those happen to be the same number? What does that equal? Well, let's turn this logarithmic expression or equation into an exponential. So that means base 5 to the question mark equals 5. 5 goes here, question mark goes here, that 5 goes over there. So what does that question mark equal, class? That's right. It must equal 1 because this is just 5. So 5 to the what equals 5 to the first. 5 to the first. So question mark equals 1. And we can say, therefore, the log base b of b is equal to 1. And the natural log of e is equal to 1. We will use especially this property right here when we do some examples here in the next video. So there's those properties as well as the other properties. Thanks for watching.